Things there. Good afternoon. From the NIH Bridge to AI program, the Bridge Center Skills and Workforce Development Core. I am Pei Ping, together with Dr. Carol Watson at UCLA. Welcome all of you to join us on this lecture regarding reinforcement learning. I'm handing it over to this training module director, Professor Wei Wang. Wei, please introduce the speaker.
Thank you, Pei. Today, we are delighted to have Professor Quanquan Gu to give a lecture on reinforcement learning. And Professor Gu is an associate professor in computer science at UCLA. And he received his PhD degree from computer science at UIUC. And before he joined UCLA, he finished his postdoc training at Princeton and also was assistant professor at University of Virginia. His research area concerns by and large in machine learning with the focus on non-convex optimization, deep learning, and reinforcement learning. And today, he will introduce fundamental reinforcement learning concept and algorithms, including a Markov decision process, rewards and return value functions, Bellman equations, and basic planning algorithms, as well as potential applications of reinforcement learning. Without any further delaying, I would hand over to Professor Quanquan Gu to start his lecture.
Thank you for the nice introduction, and thank you for having me here. Let me share my slide. All right, so can you see my slide?
Yes.
Okay. All right, yeah. So so today I will give a very concise introduction to reinforcement learning. So reinforcement learning is a big topic in modern AI. It is worth like a whole semester class to go over all the details and every single aspect of reinforcement learning. But in today's lecture, I will just give you a very concise introduction to reinforcement learning, covering the most important concept and algorithms. And I hope this will be a good starting point for you if you want to learn more materials and details about reinforcement learning. So I will start the introduction. So what is reinforcement learning, right? So many of you have heard of reinforcement learning in different application domains. So one of the most famous example or application of reinforcement learning is AlphaGo, right? Which is an AI agent that is trained using reinforcement learning to play the Go game, and it can beat the human champion actually many times. So briefly speaking, reinforcement learning is a learning algorithm that is perform the learning process by interacting with the environment. So it's a goal-oriented learning because there are some so-called goal state or terminal state. Once the learning agent enter the goal state, then it will stop the learning. And because the environment is unknown, so the learning algorithm or the agent need to interact with the environment to gather more and more information from the environment to accelerate the learning process, to guide the learning process. And within reinforcement learning, there are several key questions that the agent need to resolve. One is learning what to do, right? So this need to be defined some kind of object function, and learning how to map situations to actions. This is the task of policy learning. And the ultimate goal is to maximize cumulative numerical reward signal. So in this picture, you can see that there's an agent sitting in the middle, and there's an environment. So the agent take action, then the environment will respond to this action by transitioning to the next state, and also give the reward to the agent. And then the agent will enter a new state. And at that new state, the agent will decide what action to take. And once the agent takes action, the environment will repeat the response by providing the new state and the new reward. So reinforcement learning, as you can tell from this illustration, it's a closed loop learning process, or we say it continual learning. And the agent need to learn the policy and then use that policy to guide the learning and exploration process. And the environment is often a stochastic environment, which means even at the same state, if, for example, on the different actions, the transition between states may not be deterministic. So it's like a random or stochastic process. So there's a lot of uncertainty. And due to this uncertainty, it poses a big challenge for the agent to learn the optimal policy or to achieve the maximum possible total reward. So formally speaking, the goal of this reinforcement learning or sequential decision process is to select a sequence of actions to maximize the total reward, future reward. And the actions taken by the agent may have some long-term consequence, because the action will affect the state transition. Okay, so this is some key difference between supervised learning, because in supervised learning, there's no state, no concept of state. And the behavior of the learning algorithm will not change the state of the environment. But this is not the case in reinforcement learning, because the action the agent take will affect the state, will actually make the state transition. And another challenge is the reward may be delayed. Okay, so in other words, even the agent can receive some immediate reward, but the immediate reward may not indicate like a total reward. Okay, so it may be better to sacrifice some immediate reward to gain more long-term total reward. Okay, one example is, for example, financial investment, right? So if you want to buy like a stock, you may buy a stock that gives you a very like a short-term, for example, price increase, but this may not be the optimal investment strategy, because at the end of the day, you want to make profit or make money by buying a stock that will increase, for example, the most within, for example, in 6 months or in 2 years. And applications of reinforcement learning is very broad. One application domain is games, for example, the Go game or some video games. And another application of reinforcement learning is in the medical domain, for example, mobile health. Each person will wear some mobile device, such as, for example, Fitbit or cell phone. And the cell phone can, for example, monitor the health condition of each person, and it may, for example, recommend the person to take some exercise or take some, for example, medicine. So this is called a precision medicine or mobile health. And another application is robotic control. For example, there's a robot arm, and we want to train the robot arm to accomplish some task, for example, moving some stuff or to do some surgery, right? So this is another application of reinforcement learning. And of course, in those high-tech companies, they are also using reinforcement learning to do advertisement, for example, online advertising or recommendation systems. And more recently, many of you have heard of ChatGPT, so which is a very powerful chatbot. And one of the techniques behind the ChatGPT is also reinforcement learning with human feedback. So they will use reinforcement learning algorithms to collect the human feedback. For example, if you ask a question, it may give you several answers, and the human will tell which answer is the best answer. And using this kind of feedback, the chatbot may improve its ability or behavior in terms of dealing with question and answers. All right, so with that, I will dive into the more like a formal introduction of reinforcement learning. So there are several important concepts or terminology in reinforcement learning. One is called policy. So it tells the agent what to do. And the second concept is called reward. It tells the agent what action is good or what action is bad. And the value, which is you can think of as an expected total reward. So it will tell the agent which action is good in the long term or which action is bad in the long term. And finally, the model. So the model is also known as the environment. And the model will decide the state transition under each action. So this is something later we will use the so-called markup decision process to describe the environment or describe the model. And like I mentioned before, reinforcement learning is different from supervised learning because in supervised learning, there's a labeled training data. Given an input, it also gives you the output, the ground truth output. Then the learning algorithm will just take input and output and then fit a classifier or fit a predictor to predict the output. And the measure of success of supervised learning is to minimize the error between the ground truth output and the predicted output. But in reinforcement learning, there's no labeled training data. And also the data are no longer independent and identically distributed. The data actually are collected on the fly when the agent interact with the environment. So in this case, when we, for example, train a reinforcement learning agent, our goal is to use the reward received in the history and try to find a policy such that by following this policy, the agent will achieve as much total reward as possible. And there are some key features of reinforcement learning. For example, the agent action will affect the subsequent data it will receive. The reason is by taking different action, it will affect the state transition. And the state transition is like a random process. So therefore, the agent's action will have some long-term impact on the future data it will receive from the environment. And it is a try and error search process because the agent needs to explore, right? So at the same state, the agent may decide to take different actions because it wants to explore the unknown environment. So this is essentially a try and error search process. And also the reward may be delayed. This is something I mentioned before. And there's a very important concept called exploration and exploitation. So let me explain it to you. The agent wants to find a good policy from its past experience of interacting with the environment without losing too much reward along the way in pursuit of the optimal policy. So exploration means it will find more information about the environment, which means it may have to sacrifice some short-term reward, but instead it will have a better understanding about the overall environment. And exploitation means the agent will exploit the information contained in the historical data and then just take actions to maximize the immediate reward. So these two need to be balanced because if you just do exploration, then it may not convert you to the optimal policy very quickly. Or if you just do exploitation, then the agent will find a suboptimal policy. So in practice, we need to balance this exploitation and exploration. So there's a trade-off. To give you an example, for example, we want to select a restaurant to go for dinner. Then if you want to do exploitation, which means you just go to your favorite restaurant. Or if you want to do exploration, then probably you want to try a new restaurant suggested by, in the old days, maybe Yelp or Google. Now people may just ask ChatGPT, right? And another example is game playing. So you can play the move that you believe is the best based on the history, right? So this is called exploitation. Or you can just play an experimental move. You haven't, for example, taken this move before, but you just want to try it. Maybe this move may give you like a better chance to win the game. So this is called exploration. Okay. So with all this high-level introduction to reinforcement learning, now I'm going to narrow down to the mathematical foundation of reinforcement learning. So I will start to introduce the mathematical model of reinforcement learning, which is called the Markov decision processes. So here's a list of notations that I will repeatedly use in the remaining of this lecture. So I will use this uppercase symbol X to denote a random variable and use lowercase x to denote the value of a random variable. And the P of X equal to this X, capital X equal to this lowercase x means the probability of a discrete random variable X taking value X. And this E of X is the expectation of the random variable. And without the loss of generality, I will just use this capital T to denote the length of the episode. And in this lecture, I will mainly focus on infinite horizon discounted Markov decision process, which means there's only one episode, but the length of this episode can be infinite. And I will use this script S to denote the state space, which is a core concept in reinforcement learning, but not in supervised learning. And use this script A to denote the action space, which contains all the possible actions or moves that the agent can take at each state. And finally, I will use this transition probability. So this is a conditional probability of next state S prime, conditioned on current state S and the action the agent take at the current state A. Okay. So before I introduce the formal definition of a Markov decision process, let me give you an example of a very simple Markov decision process. So in this example, there are two states, the start state and the stop state, so two states. And at the start state, the agent can take one action, which is called a search. Okay, and by taking this search action with probability 0.1, the agent will remain at the start state and receiving reward -1. And with probability 0.9, the agent will transit to the stop state, receiving reward 0. And similarly, at a stop state, there's one action that the agent can take, which is the carry action. And by taking this carry action with probability 0.5, the agent will remain at the stop state, receiving reward 1. And with probability the other half, the agent will transit to the start state, receiving reward -2. Okay, so this is a very simple and toy example, but I hope from this example, you will have a basic idea about what MDP is. And we can describe this state transition probability just by reading those numbers from this state transition graph. Okay, so with this example, now let me provide more like mathematical details about the Markov decision process. So first of all, I will define the so-called Markov property, or first order Markov property. A stochastic process ST is a Markov if and only if, for example, the conditional probability ST+1 conditioned on the history. History means from S0 to S1 to S2 and to ST. So this conditional probability will equal to the conditional probability of ST+1 conditioned on ST. So the meaning of this equation is the future of the state actually is independent of the past given the present. Because ST+1 is the future, ST is the present, and S0 to ST-1 is the past, is the history. So Markov property means the future only depends on the current, the present state. The future is independent of the past, conditional on the current state. So that's the meaning of Markov property. And with this Markov property, we can define a Markov process, which is a tuple of S and P. So S is the set of state, or we call it the state space. P is the state transition probability. So it's a conditional probability of ST plus 1 conditional ST. So the transition in this Markov process actually satisfies the Markov property, and we will use this P as prime, this shorthand notation to denote this state transition. And we assume that the state transition is stationary or time invariant, because you can see that this P as prime does not depend on the time step T, which means no matter what T is, this transition from one state to the other state, that probability will remain the same. And the transition probability can be represented by a matrix. And this matrix representation might be useful later if we do, for example, value iteration. We can do value iteration in a matrix form. And in previous example, you remember that, for example, there are two states, start state and stop state. For that two state MDP, actually we can define we can describe the state transition probability using a 2x2 matrix. So for example, from start state, the probability of transition to start state equal to 0.4, and the probability transiting from the start state to the stop state equal to 0.6. Okay, so this matrix need to satisfy is a stochastic matrix. In other words, if you sum up the probability at each row, it should equal to 1. And the Markov decision process is a generalization of a Markov process. So here, decision actually means action, right? So we will just augment the Markov process by adding additional, for example, action space, the reward R, and the discount factor R. So here, S is a state space, A is action space, P is the state action transition probability. So different from this just the state transition probability, this state action transition probability is the conditional probability of ST plus 1 conditional ST and AT. So this conditional probability need to condition both the current state and the action the agent takes at the current state. So we will use this shorthand notation P as prime of super A to denote this state action transition probability. So S is the current state, S prime is the next state, the future state, and A is the action the agent will take at current state. And this capital R is a reward function. It can be like a stochastic, can be a random variable or random function. So therefore, we will define the reward as the expectation of the reward function. For example, at the current state S, taking action A, condition on these two, we take the expectation of the reward function, and this will give us the expected reward at the current state S by taking action A. So we use this R sub S sub A to denote the expected reward. And the gamma is a discount factor, and the meaning of why we need to introduce this discount factor will be immediately clear in the next slide. So in R, there's a reward, which is the incentive the agent will receive immediately by taking action. And there's another important concept called return, which is the total reward. Okay, and actually the return is the goal of reinforcement learning, to maximize the return instead of to maximize the immediate reward. Because for some policies, even though it can bring you very high immediate reward, but in long term, the total reward may not be the optimal, or may not be the highest. So the ultimate goal of reinforcement learning is to achieve the expected total reward or expected return. Okay, so here the return is defined as the summation of the reward. But when we do this summation, we will introduce some discount. The reason why we want to introduce discount is because a high reward received in the future may not be as valuable as a the same reward received in the short term, right? So we still prefer to receive high reward in the short term instead of in the long term, right? So that's why we add a discount factor. So if this discount factor equal to 0, then that means we just care about the immediate reward. That's okay. But if for example, the discount factor gamma equal to 1, which means we consider the future reward and the immediate reward equally. That's also okay. But in practice, actually, we often choose gamma, which is strictly between 0 and 1, because we still want to discount the reward in the future. Okay. And another concept I mentioned before is policy. So what's the mathematical definition of policy? So policy is just a distribution of action over some state. So we use this pi a given s to denote the policy, which could be like a stochastic, which could be a distribution. Okay. And the policy is a stationary if this distribution is a time invariant. And a special case of stochastic policy is called a deterministic policy, which means at each state, you just take one action deterministically without any randomness. Okay. And then we can define the value function. The value function is the expected return by following some policy pi starting from some state s. Okay, so this pi sub v sub pi of s is the expected return starting from state s by following this policy. And this expectation actually is with respect to both the policy and the state transition probability of the underlying MDP. And another value function is called the action value function, or sometimes people just call it the Q function. And this Q function is exactly the Q when people talk about the Q learning or deep Q networks. So that Q is this Q. It's essentially action value function. So for action value function is the expected return from state S by taking action A and following the policy pi. Okay, so the difference between value function and the state and action value function is for action value function, we need to specify the starting state as well as the starting action. Okay, so then this Q pi SA will tells you the value that the agent can receive, or the expected return the agent can receive starting from state S taking action A. And with the definition of the value function and action value function, we can derive the so-called Bellman equation. So I believe many of you have heard of Bellman equation. It's named after the statistician Richard Bellman, which is a central concept in dynamic programming and reinforcement learning, because many algorithms actually are derived from Bellman equation. So Bellman equation is as follows. So briefly, so at a high level, Bellman equation tells you that the value function at state S by following policy pi can be written as the expected immediate reward if you take action A at current state S, and the expected value of next state. Okay, so this outer summation actually is the expectation with respect to the policy, and this inner summation actually is the expectation with respect to the state transition probability. So using Bellman equation, it can connect the value at the current state and the value of the next state, and also the immediate reward the agent will receive by taking a certain action. Okay. So this is the Bellman equation for the value function, and similarly, we can derive the Bellman equation for the action value function, or for the Q function. We just remove this expectation outer summation with respect to the stochastic policy. Okay. And since we defined the value function by following policy pi, then we can also define the optimal value function. So optimal value function is the value function if you do maximization over the policy pi. Okay, so you can see that this V star of S is the maximum value at state S by maximizing over all possible policies. Okay, so and the resulting policy that achieves this optimal value is called the optimal policy. And similarly, we can define the optimal action value function, which is the optimal action value that by maximizing the action value function over the policy. Okay. And let me give you an example of optimal action value function and the optimal policy. Okay, so this Q star SA, because there are only two states, 1 and 2, and also only two actions, 1 and 2. So the optimal action value function can be represented by a 2x2 table. And from this 2x2 table, if I ask you to tell me what is the optimal policy, so in other words, what's the action the agent should take at each state, now you can see that at state 1, right? If you take action 1, the value is 4. If you take action 2, the value is 5.4. So apparently, the optimal action at state 1 should be action 2. And similarly, the optimal action at state 2 should be action 1, because action 1 gives you higher value. Okay, so in other words, once you calculate this optimal action value function, you can immediately tell what's the optimal policy. And for optimal value function and optimal action value function, there also exists a Bellman equation, which is called a Bellman optimality equation. So the difference between Bellman equation and here Bellman optimality equation is instead of taking expectation over the policy, we just take the maximization over all possible actions. So in other words, here we just find the optimal action instead of taking expectation of the stochastic policy. And the relation, this is a recursive form. So Bellman optimality equation basically connect the optimal value function at the current state S and the optimal value function at the next state S prime. Okay. So later, I will derive the value iteration algorithm from this Bellman optimality equation, and you will see how useful this equation is. Okay. So now I'm going to move into the last part of this lecture, which is about the algorithm. Okay, so we have introduced the basic concept, the MDP, the return, the value, and the Bellman equation. Now, given all this basic concept, then a natural question is how to find the optimal policy. Okay, so this is about planning. Okay, and we will use the so-called dynamic programming algorithm to find the optimal policy. So what is dynamic programming? So dynamic programming is an algorithm which is embedded in operation research and also in algorithms. So it's a method for solving complex problems by breaking the problem into many sub-problems. And it will first solve the sub-problems and then combine solutions to the sub-problems, get the solution to the whole problem. Okay. So dynamic programming is a very general solution method for problems which has two properties. One is that there's an optimal substructure, and there's a principle of optimality. And as you recall, the Bellman optimality equation immediately give you these two structures, right? Because the Bellman equation gives you a recursive decomposition. The value of current state is equal to the value of the next state using that recursive form. And also the value function will store and also reuse all those solutions. So, so the Bellman equation actually enables us to use dynamic programming to find the optimal policy for reinforcement learning. And because this is just a very introductory course, so let's assume the transition probability of the MDP is known. This is a very strong assumption, and but in the future, there's also many algorithms that can deal with unknown transition probability, but I'm not going to cover in today's class. So given a market decision process, for example, state action, transition probability, reward gamma, discount factor, we want to, and also a policy pi, we want to evaluate the policy. to calculate the value for this policy. This is called a prediction. And another problem is called a control. Just given the MDP, we want to find the optimal value function, V star, and optimal policy pi star. Okay, so we will talk about both the prediction problem and the control problem. So I will first introduce the policy iteration algorithm. So this algorithm, the input is a policy pi. We want to evaluate. So basically, we want to ask the algorithm to tell us how good this policy is. And from the Bellman expectation equation or Bellman equation, we can write down this recursive form. V pi of s is related to V pi of s prime. And the algorithm will just do fixed point iteration. So from some initial estimate of this policy, value function under this policy, let's say V pi 1, okay, we will repeatedly do fixed point iteration to get V pi 2, and then V pi 3, and until maybe some huge number or even infinity. And we can prove that if we do this fixed point iteration, this V pi t sequence will converge to V pi, which is the value function under this policy pi. And this fixed point iteration actually can be derived using this vector and matrix form, which I will probably just skip because it's a little bit too technical. But instead, I will give you an example of running this this policy evaluation algorithm using on this grid word example. So this is a 4x4 grid word, and there are 14 states which are non-terminal state. But this state in the top left or this bottom right, these are two other terminal states. And suppose there's no discount, so in other words, gamma equal to 1. And there are 4 actions at each state, just to go up, down, or left, right. Or you can think of north, south, east, or west. And then the action, if you, for example, at a state which is at the boundary, if you, for example, go right, then it will remain at the current state. It cannot, because it cannot go beyond this boundary. Or if the state is at the left, if you go left, then it will still remain within this grid word example. And we just consider the random policy. So in other words, at each state, the agent will take 4 different actions with equal probability 0.25. And we just want to evaluate how good this random policy is. Okay, then we just do preface this policy evaluation algorithm, which is derived from the Bellman equation. So we start from like initial guess. That's all 0. Let's assume all the value at all the state are equal to 0. And then we just do value iteration to evaluate the random policy. And after 1 iteration, you can see that the value is updated. Okay, some of them become -0 or -1, and then after 2 iterations, value of some entries get further updated. Okay, some of them become -1.7, some of them become -2. And after 10 iterations, you can see that the value at a different state actually is very different from the initialization. And if we run infinite number of iterations or many iterations, the value function will converge to this one. And you can see that this is -14, -20, or -18. You can think of this is the how many steps the agent will take before it converges to the value of that policy. Okay, because after each action, it will receive reward -1. So if I tell you the value of this state is -14, then this probably just tell you that how many action or how many steps the agent need to take to get to that value. Okay. And now we have a method to evaluate the policy. Okay, which is value iteration. then we can think about if I can evaluate the policy. Once I get the value function for that policy, then if I can improve that policy, the answer is yes. So once you get the action value function for certain policy, we can just take this greedy policy to get a new policy pi pri. Okay, so this pi pri is a greedy policy we derived from the action value function of a current policy pi. So in other words, once you have a policy pi, you do this policy evaluation to get the value for this policy, and then you take a greedy policy to get an improved policy pi pri. And this process can be repeatedly called. One is called the policy evaluation, the other is called the policy improvement, and together it is called the policy iteration. Okay, so this is exactly the algorithm of policy iteration. So within the policy iteration algorithm actually is like a loop, right? And at each step, we first evaluate the policy pi to get a Q pi SA, and then we improve the policy pi to get a pi pri. And this process will be repeated for many iterations. And we can show that under certain conditions, if you do the policy iteration will converge to the optimal policy. Okay. So this is an illustration of a policy iteration. You can see that starting from some initial policy pi, we first do policy evaluation to get the value function or action value function of this policy pi. And then we take greedy policy to improve the policy pi to pi pri. And then we do policy evaluation for pi pri to get the value function for pi pri. And then we improve pi pri to get a pi, maybe double pri. So this is like a repeated process. And you can see that after many iterations, this initial policy pi will be improved to the optimal policy pi star. Okay, so within policy iteration, there are two key steps. One is called the policy evaluation. The other is called the policy improvement. Okay, and both of them can be done very easily. So for policy evaluation, we just do the value iteration algorithm we derive from the Diamond equation. And for policy improvement, we just do the greedy policy. Okay, so I hope this is clear, and it's very easy to implement. But one thing I want to mention is here we assume the state transition probability is known. So that's why we can write down this fixed point iteration, because it relies on the knowledge of this state action transition probability. If the state action transition probability is unknown, then we need some other method either to estimate it or to get around of it. Okay, that would be more challenging setting, which I'm not going to cover in today's lecture. Okay, so here's the algorithm for policy iteration. You can see that it's a loop algorithm. And the first step in the loop is to do policy evaluation based on this value iteration. Okay, so from some initial V0 of S, we use this fixed point iteration to evaluate the value of the policy pi until some convergence criteria is satisfied. And then we are using greedy policy to improve the current policy. Okay, and this step 2 and step 3, these two will be repeatedly called until the convergence. Okay. Okay, so in the remaining maybe 5 minutes of this lecture, I will introduce the other equally important and also equally useful algorithm, which is called the value iteration. Okay, so value iteration just want to find the optimal policy directly. So instead of first start with some random guys and then evaluate that random policy and then do improvement. So this is what the policy iteration does, right? For value iteration, it won't divide this process into, for example, evaluation and improvement. It will just directly go find the optimal policy. So how does the value iteration achieve this goal? So remember that beside the Bellman equation, we also have the Bellman optimality equation, which is this one, right? And this one also enjoys a fixed point iteration or fixed point based algorithm to find this V star. So what we do is we start with some initial guess of the optimal value function. We call it V star super 1. And using the fixed point iteration, we'll get V star super 2. And then after many iterations, we hope this V star T will converge to V star. And this is indeed true because we can show that under certain regularity conditions, if we do fixed point iteration induced by this Bellman optimality equation, the optimal value function can indeed converge to the optimal value function. Okay, so this estimated optimal value function can indeed converge to the optimal value function. Okay, and unlike policy iteration, there's no explicit policy we will introduce or we will maintain during the value iteration. Okay, so this might be the advantage because it will save you a lot of example effort by calculating or improving the policy itself. So again, we can derive the fixed point iteration or fixed point equation from the Bellman optimality equation. So here we need to introduce some vector and some matrix. And in the interest of time, I will just skip this slide because I don't think it will affect your understanding of value iteration. But this is just some detailed quantities that you need to define, and also you need to play with when you implement this value iteration algorithm. Okay, so let me give you an example of value iteration, which might help you better understand this algorithm. So suppose we have two states, state 1 and state 2. And at state 1, you can take action A, you can take action B. And at state 2, the agent can take action C or can take action D. Okay. So if you take, for example, at state 1, if the agent take action A, then with probability 0.7, it will remain at state 1, receiving reward 2. And with probability 0.25, it will transit to state 2 and receiving reward 2. Okay. At state 2, if the agent take action C, with probability equal to 1, it will remain at state 2, receiving reward 2. And if the agent take action D, it will deterministically transit to state 1, receiving reward 3. Okay. So from this state transition graph, we can just write down those key quantities such as expected reward, the state action transition probability, like deterministically, okay, from this state transition graph. And here, without the loss of generality, we assume this count factor equal to 0.5. Okay. So given this number, we can do value iteration. So the initial estimated optimal value are all 0. Okay. And then from this all 0 initial guess, we will just repeatedly call the Bellman optimality equation. Because at initialization, these two are 0, so these 4 quantities all equal to 0. So V2 of 1 actually equal to R1A, which is equal to 2. And the other one, R1B, which is also equal to 2. If you take a maximum, then it's still equal to 2. And similarly, this V star of 2 at step 2 equal to 3. So this is after 1 iteration. And let's do another iteration. Now, we have this V star 1 at step 2. So we plug in these numbers into the Bellman optimality equation. Then we can get V star 1 at step 3 and V star 2 at step 3. So here, the number in the parentheses, okay, is the state because there are 2 states in this example. And the number in the superscript is the index of the iteration or number in value iteration. Okay. And the other quantities actually are just pre-calculated here, which can be read out from this state transition graph. So after 2 iterations, the optimal value function the estimated optimal value function for state 1 equal to 3.5. The estimated optimal value function for state 2 equal to 4. Okay, so we can just apply this iteration again and again. Then after many iterations, this two-dimensional vector will convert it to like a constant vector, and each entry of that constant vector just tells you the optimal value function for state 1 and state 2. Okay. And then you may ask, since I directly calculate the optimal value function, then how can I figure out the optimal policy? Okay, so this is very straightforward, because from the optimal value function, if you just do one step, look ahead, in other words, you just call the Bellman optimality equation again, then you can doing this maximization over action, then you can immediately figure out the optimal policy, which is a greedy policy. Okay, so so that's how you derive the policy after you finish value iteration. All right, so this is the algorithm flow for value iteration. You can see that the structure actually is simpler than the policy iteration, because in policy iteration, there's an outer loop, and there's also inner loop, because the inner loop will be used to evaluate the policy. But for value iteration, there's just outer loop, and then we just do this value iteration, starting from some initial estimate of the value. We do value iteration, we get the optimal value function. And after we get the optimal value function, we do one step, look ahead, then we can calculate the optimal policy. Okay. So with that, I will just wrap up here. So from this lecture, we've learned Markov decision processes, which is the underlying mathematical model for reinforcement learning. And we've seen the definition of reward, the immediate incentive, and the return, which is the total reward, the cumulative incentive, which are the central goal of reinforcement learning. And I also introduced the value function, including state value function and action value function. And the value function enables agent to evaluate how good a given state or action is in terms of its expected total reward. And based on the definition of value function, we can derive the Bellman equation, which plays a central role in reinforcement learning, because it provides a recursive relationship between value at different states. And this recursive relationship enables us to use dynamic programming-based algorithm to calculate the value function. And finally, I just introduced two basic planning algorithms. One is called a policy iteration, which consists of two sub-steps, sub-module. One is called policy evaluation, the other is called policy improvement. And the other algorithm is even more simpler, which is called value iteration. Okay, and both of them can be used to find the optimal policy in reinforcement learning. But both of them relies on the knowledge of the underlying state action transition probability. What if the state action transition probability is unknown? Then we need more additional techniques to deal with that, which is beyond the scope of today's lecture. Okay, so and I want to say that some of slides are from Dr. Traba's tutorial slides, and also some slides are borrowed from Dr. Richard Sutton and Dr. David Silver's lecture slides. And with that, I will stop here, and I'm more than happy to take questions from the audience.
Thank you, Professor Gu. And we have, for the audience, please submit your question at the Q&A panel. So we now have one question coming in. How do we formulate the reinforcement learning program if we know only the initial and the final states, S0 and Sn, but not the entire state space? What are some potential ways to construct the state space from data or through exploration?
Yeah, thank you. That's a great question. So if you know what is the initial state and what is the final state, you probably know what are the, for example, features, or what are those, for example, covariates you have at the initial state and the final state. So you should consider this state as like some kind of a representation of the underlying problems. For example, at the initial state, let's take, for example, personalized precision like medicine as an example. Suppose we have some mobile devices on the patient, and we can collect for example, the heart rate or many other like information, and all this information you can put them together to define a high-dimensional vector, and this high-dimensional vector can be considered as the state of the patient, which is exactly the state of the reinforcement learning that we will define when we do this modeling. And you can imagine as, for example, as we, for example, use different strategies, different treatment strategies or different actions, the policy will suggest the state of the patient may change over time, but you can actually get access to those states from the sensors data or from the patient. They can, for example, report what their, for example, how many minutes of exercise or what kind of diet they take each day. So in other words, once you know the initial and final state, actually you already know how to define the state. And if you know how to define the state, then the state between 0 and n actually is obvious.
Thank you. I do have a follow-up question of that, right? So, thinking about the medical domain, right? So for disease, right? There are some like, completely healthy, right? So, and there's also like a terminal state like death, right? And for some disease, there's a well-defined different stages, right? And but for some other disease, it was not very clear, right? So the boundary between different states. Think about that maybe like in a continuous space, right?
Yeah.
So in that case, what would be maybe some guiding principles, like how people can formulate the disease?
I see.
States.
Okay, yeah. Thank you for the question. Actually, it's also helped me clarify the questions by one of the audience. So in this introduction, I assume the state actually is like a set of discrete states, right? But in applications, the state actually may not be a discrete space. It can be a continuous space. Then we need to represent the continuous state space using some compact representation. And this is the place where, for example, deep learning or some kind of representation learning algorithm can help. For example, the key technique behind the deep reinforcement learning is to use the neural network to, for example, to represent the policy or to represent the state. So if the state, for example, is continuous, contains many different information such as the lab test result, for example, the doctor's clinical note or the patient's self-reported status. So all those information may contain both textual information, numerical information, categorical information, or even some imaging data, right? So they are heterogeneous and multimodal. And in order to use all those information to define a state, then we probably need to use a neural network to map or to integrate all these different kind of information into a high-dimensional vector. And then this high-dimensional vector can be considered as a state or can be considered as a dynamic signature of this patient, and it may change over time. So this is how we deal with continuous state space in practice when we do RL. Yeah.
Thank you, and for the thorough answer. I see no further questions from the audience, and we're also at the hour. So thank you so much for this lecture. So we learned a lot, and I'll hand over back to, I see Peipei is still online. So
yeah, thank you for having me. Thank you.
See a few words. I guess Peipei maybe
I'll just say thank you so much, Dr. Gu. These are really such important concepts, and thank you for so clearly defining these things for our learners. This is fantastic. Thank you so much.
Thank you. My pleasure.
Thank you.
Yeah. See you. Bye.
Thank you. Bye-bye.